So, how does the Schrodinger equation comes from? Richard Feynman has said that. Where did we get that from? Nowhere is possible to derive. It's not possible to derive it from anything. You know, it came out from the mind of Schrodinger, which means that we don't really have a solid reason why the Schrodinger equation look like this. But the fact is that Schrodinger equation can describe many phenomena that the classical mechanics cannot be able to do so. So it exists because it really works. So, and the foundation of the equation is structured to be a linear differential equation based on classical energy conservation and consistent with the de Broglie relation. So in this chapter, we introduce the de Broglie relation first, then we enter the Schrodinger equations part. The solution of the wave function is phi, which contains all the information that can be known about the system. Which means that he knows everything, but he don't really, the wave function does not really have a physical meaning. However, it can tell you many things, which is useful to you. And actually, how does the Schrodinger equation comes from? There are basically two postulates. So the first one is the plane wave assumption. We assume the solution to be a plane wave, and then we try to derive an equation that the solution is the plane wave, and then we try to find the equation whether it has more meaning that are really interesting. The physicians do it like this. And the second postulate is the de Broglie relation, which is the momentum P equals h bar k, and also the energy operator E equals h bar omega, which is you can consider it E equals hf. So first of all, we need to know something about the momentum operator. Momentum operator means that it's of course an operator, but operator means when we have an operator add on the wave function, it really tells you what the momentum is. Momentum operator is just like, I try to ask the wave function, please tell me the momentum operator. Then after this operation, the wave function doesn't change, but it pops out the momentum of it. Then this is the concept for the momentum operator. So we want to make it just output h bar k for the momentum operator. And as we observe the wave function, which is a plane wave, how it can prop out the h bar k. So we just ignore this part. We observe this part. How can it prop out the k? So we just take derivative with respect to x, then it will pop out ik. So the first step is to take the first derivative of with respect to x, then it will pop out ik. Then we want to make it to be h bar k. So this is I, so we divide by I, and we want an h bar, so that we multiply an h bar, and that's how we construct the momentum operator. That's how we construct the momentum operator. So this is the momentum operator. This one act on the plane wave, and it will tell you the h bar k. So this language comes from the linear algebra. So This one, the exponential, the plane wave, we call it the eigenstate of p hat, the momentum operator. And h bar k is actually the eigenvalue. If you have learned the linear algebra, you know that the eigenvalue means that when you have vector, when you have a square matrix, when you have a square matrix, when you have a square matrix A, if it multiply a vector V, but for some specific V, then it will something like you multiply by a eigenvalue, and then you have the original vector. But for most of the case, the vector will rotate to another direction. But for some certain direction, when you multiply this matrix to a vector, then the direction of the vector doesn't change. You only scale the vector. So lambda is called the eigenvector in linear algebra, and this is called the eigenvector. This is eigenvalue, this is eigenvector. And here we also call h bar k is the eigenvalue of the momentum operator. So first of all, we try to generate the momentum operator. And next, we generate the energy operator according to this de Broglie relation about the total energy, And in quantum mechanics, we don't call it the E operator, we call it H operator, which is called the Hamiltonian. If you learn the Lagrangian mechanics, then you may know this term, which stands for the total energy of the system. And likewise, we want this Hamiltonian operator add on the wave function, which will tells you the energy, the total energy of the plane wave. So we want to have omega. So when we observe this one, we try to take time derivative to the plane wave. So we take the time derivative, we will have minus I omega here, minus I omega here. So we multiply I so that this will become 1, and we need an additional h bar so that we multiply h bar, so that we know that the Hamiltonian or the energy operator is look like this, IH bar partial t. So next, second step, we get the energy operator. So next is the kinetic energy operator. Kinetic energy. So actually in classical physics, we know that the kinetic energy is nothing but 1/2 mv squared. But here we write it as p squared over 2m. P squared over 2m, which is actually the same. We multiply an m here, divide by m. So that mv is p, so p squared on the top and 2m on the bottom. And as we know, k, the kinetic energy operator, should give you the p squared over 2m. And here we know that the momentum operator will give you the momentum. So that we let the kinetic energy operator to be the composite of 2 momentum operator divided by 2m. Then it should give you p squared over 2m. And we substitute the momentum operator here, h bar over I partial x, h bar over I partial x. Then this one will be a second derivative with respect to x. We have a h bar square, and I square will be -1. So we have -1 and 2m. So the kinetic energy is something very tricky, which is minus h bar square over 2m partial x squared. which is negative, very interesting. But actually, we have also the kinetic energy operator. So according to the classical physics, we know that the total energy should be equals to the kinetic energy plus the potential energy. So if we make it like this and h bar, h hat act on the wave function, k plus u also act on the wave function, they should be satisfied according to the classical physics interpretation. And U is the potential energy. U is the potential energy, and it is actually a function of x. And some of the literature, they would like to use V instead of U, but in this textbook, U is used for potential energy throughout the textbook. So here we still use U for the potential energy. And we substitute the Hamiltonian here. This is the kinetic energy operator, and this is the U, which is just a function. You can manipulate it just like what we learned, like the potential step or the barrier. This is related to the environment. So these equations should be satisfied, and this is actually the general form of the Schrodinger equation, which is related to the space and time in one dimension. If we write it in 3 dimensions, this one is the same, and this is second derivative with respect to x, so it changed to Laplacian, something similar to the wave equation. And this is the Schrodinger equation in 3 dimensions. But it is not really the same as the one we saw in the textbook, because it is only the time-independent case. So similarly, we use the separable of variable, which means that the wave function can be separated into the space function and the time function. And we substitute this one into the Schrodinger equation. So substitute inside, and then phi of x is independent to t, so it can factor out, and phi of t is independent to x, so phi of t can be factored out. And we can also separate the variable. We just divide phi t and phi x on divide on both sides. Then the left side, it will look like this. This side, it will look like this. And this one is a function of t. This one is a function of x, and they are equal, so that they should be a constant. And the dimension of this constant is actually the energy of the system. So that we can separate the Schrodinger equation into 2. The first one is this one. The first one is this one, and this one. So when we solve it, it will be nothing but exponential to I omega t, which is just shown in the slides. It already assumed that the time dependent part is look like this. And we also find that we will get E over h bar equals omega, or E equals h bar omega, which matches the de Broglie relation. For the second one, we multiply this term to the right hand side. It will look like this, and we move this term actually we move this term and this term to the right. So we'll have E minus U here, and this is a minus, so this become positive. So finally, we get the equation like this, and as long as we divide h bar squared over 2m for the whole equation, we will get this one. This is the time-independent Schrodinger equation, which we have saw it in on the textbook. So that's how this equation comes from. Okay, so starting from the plane wave as a solution, the Schrodinger equation is derived. There are some postulate. You cannot really explain why this postulate is true, but as long as the Schrodinger equation can explain or predict many phenomena in the quantum world, then it is valid up till now. So and you can also find it the Schrodinger equation is linear, which means that if phi1 and phi2 are two solutions to the Schrodinger equation, then alpha phi1 plus beta phi2 is also a solution to the Schrodinger equation. You have learned the signal and system in chapter 1 or 2. It tells you what is linear, so that is a good practice to show that Schrodinger equation is linear. So here we can write that if this one is a plane wave, this one is another plane wave. This one should be 2. This one should be 2. This one should be 2. So these two are two different solutions with different k1, k and omega, k1 omega 1, k2 omega 2. So that as the Schrodinger equation is linear, and this one is for sure two solution for the Schrodinger equation, so that this one is also a solution to the Schrodinger equation. But how about if there are many wave functions with different different k's? Maybe we just finish the final part. Finish it here. This is the last page. So as long as two solutions can be added together to form the new one. So how about if we add finite many solution? So as long as we have different k and omega is the function of k, which means that with different k, the omega is different. So we have many different plane wave, and alpha beta will be the coefficient for this wave function. So for different k, we have different coefficient. We call it phi k. We call it phi k. So that we add all of them together. But this is continuous, so that we use an integral rather than summation. So in this case, the total wave function will look like this. And this is actually so we can just separate these two terms like this. And actually, when we regard this one is a term, which is a function of k. This one is actually a function of k. So this is actually the Fourier transform or inverse Fourier transform. This is an inverse Fourier transform. Or in quantum mechanics, we usually divide it by square root of 2 pi, so that there will be no normalized factor between them. Because if you just have one for the Fourier transform and 1/2 pi for the inverse Fourier transform, then the power between these two domains are different. So in quantum mechanics, they try to equalize them so that for both Fourier transform and inverse Fourier transform, they just divide it by square root of 2 pi. So here we'll write it like this. So this one is actually the Fourier transform of X domain. The K domain is the Fourier transform or inverse Fourier transform of the K domain. And if we just fix it, if the wave function is time independent, we just let t equals to 0, phi x is actually the Fourier transform of phi k. And this makes the plane wave postulate making more sense, because actually we can use many plane wave to construct different kind of function, which also satisfy the Schrödinger's equation. So the importance of um, uh, uh, which means that the doubt for assuming a plane wave postulate is become less and less, because many plane wave can really construct different kind of wave function as long as it is Fourier transformable. So this is what we need to cover in this semester.